Okay, so previously we talked about signal in time, right, and in frequency. So either time domain waveform or frequency domain Fourier series or Fourier transform. So today we have another totally new viewpoint to look at the signals and also systems. That is from viewpoint of statistics, right, and probability. So we would like to talk about spectral density and correlation. So especially useful for random signals, for example, noise, right, noise, and the communication channel. So in chapter 4, we're going to go through those important topics. Right now, we talk about two signals, right? Two catalogs of signals, power or energy. So for energy signal, we have energy spectral density. For power signal, we have power spectral density. So this one is one of the most popular things, right? we use. Then we talk about a very special signal, time varying noise, and this one's spectral density. Okay, then we done with spectral density, go to correlation. So for correlation functions, we have correlation for power signal, right? Properties of correlation. Then we talk about correlation for energy signal. Then we go to special signal, noise again. We're going to talk about band limited, white noise. So what is a white noise? What is the bandwidth for this kind of noise? So those are the things we are going to cover. Generally, two things, right? Density and correlation Okay, problem, question. So we start with spectral density. Okay, number one, for energy signal. We just finished this one, right? Transfer theorem in chapter 3. So we can find signal's energy in time by doing the time domain integral. It also can be calculated in frequency domain. So this is my Fourier transform, right? Magnitude square. So this one gives us a hint, right? So integral in frequency gives us energy. So we're going to call this one energy spectral density, right? Later we talk about more details. So this is the first equation in our textbook in chapter 4. Okay, let's look at the second one. Voltage, time, current, we get power, right? Integral the power, we get energy, right? We get energy. So this is what you have learned in your tutor class. Any problems? Any questions? Okay, now a little further. So we have two sets of equations, like 4.3, A and B. If the signal f of t is voltage, right? So we know V squared over R is my power. Integral power, we get energy. So this is what we do in time. Frequency, almost the same. So your voltage signal's magnitude square, integral it, right, over R. We also get energy when your signal is voltage. Similar to voltage, if my signal is a current signal, I square times R is my power. So I can also get my energy in time domain integration. So right, here is I square times R. So those two sets of equations came from previous slide, 4.2. Any follow-up questions?
So, when we calculate the energy, like Why do we use a conjugate of the current? Why do we use a conjugate of current?
Conjugate current. So generally, in your, yeah, I'm not sure. So in your previous experience, right, current or voltage is a real number, right? It's a real number. However, if we consider it's a complex number, we always have one. So look at here, right? We have the absolute value square. I didn't write f square. The reason is should be ft times ft conjugate if my signal is complex. If it's real, ft's magnitude square should be the same. So we write v, p, and iq conjugate. We cover both cases. If your signal is real, right? If my current is real, just Vt times It. Okay. Now here comes the very important concept: energy, spectral density. Right? Previously we showed several equations: integral f omega absolute value square over omega, we get energy. So we call this one energy spectral density. So just a definition. Okay, very soon I will show one example. Now, signal, an energy signal will pass a system. So this is my input. This is my output. We are going to connect output and input with frequency response, right? Or h omega of your system. So how can you connect them together? A quick review. We have a system, LTI system. FT, YT, GOT. In chapter 3, we talk about output of our LTI system will be input convolution with your impulse response. So this is in time. In frequency, we have F omega, G omega. Okay, in frequency, we have much easier relationship. So output signals Fourier transform is input signals Fourier transform time, frequency response. Okay, those two, they are Fourier transform. So H omega is Fourier transform of your impulse response. Now we have the third relationship in terms of spectral density. So energy, spectral density. This is my input signal's spectral density. This is output. Okay, the equation is over there, right? So now you can view your system in time, in frequency, or in point of view of spectral density. And we are going to use one example to show how to play with this equation. Now, if we know density, right? If we know density, integral your density, we get power. I'm sorry, we get energy. Okay, so those two equations we are going to use shortly in our next example. Okay. Example 4.4.1. I'm going to erase this part. You're done with this one, right? Okay, let's look at this problem. And I'm going to write something over that. So we have a signal, Ft. Ft is a voltage signal. And Ft is E2 minus 5t ut. This signal is passing a ideal low pass filter. So signal system, right? Let's look at how about this system. The system is gain of unity. Frequency, the bandwidth is 5 radian per second. And the resistance level is equivalent to a 50 ohm resistor. We want to calculate two things. The energy of input, energy of the output. Okay, this is my input, right? E2 minus 5t ut. So we know it's decreased, and because of ut, we only have signal from 0 to infinity. So this is input. My system. Okay, for the system, we know the frequency response because this is a low pass filter, right? 5 minus 5, 1. So my system is an ideal low pass filter. Cutoff frequency or bandwidth is 5 radian per second. The amplitude or the gain of this filter is 1. Okay, problem. Okay, energy of my input and output Oh, R is 50. R 50 ohm. So the equations we are going to use are over here. So this is for output. This is for output signals energy. We need to calculate 1, 2. Then the integral gives us answer. Okay, let's go through it step by step together. Okay, for input signal, almost the same as your homework. Okay, so let me show you. This is the one we're going to use. It's wattage, right? It's wattage. So I'm going to use here 4.38 to calculate my input signal's energy. Okay, so original signal integral shoot the entire time domain. Now I change it from 0 to infinity. The reason is, right, I only have positive time domain. And e2 minus 5t square, what is this one? e2 minus 10t. Okay, any questions, problem for this one? So I substitute my R into it, my Ft into it. But now just calculate this figure. So we have minus, right? Now substitute t with 0 and infinity. Put minus sign here. So 500. 500. How about e to minus infinity? 0. E to 0 is 1, right? Is 1. So we get 0.002 joule. This is my input signal's energy. Any problem, question? So I give you more detailed steps compared with the textbook. Now let's look at the output of my system. What do I need? So I do need my input signal's Fourier transform. So let's look at here. Okay, check your table. What is this one's Fourier transform? This is not, if it's not number 1, it will be number 2, right, in your table. So this one's Fourier transform is 1/5 plus j omega. So I know my Fourier transform of the input. So I know this one. Just one step further, right? 2 magnitude square. Now, we can just use this one. If my signal is complex, absolute value of magnitude squared should be signal times its conjugate. So my case is at the same. So this is the F omega. F omega. So F omega conjugate, my final result for input spectral density is 1/omega squared plus 25. Okay, now we want to look at system, right? System frequency response, absolute value square, because magnitude square response. So this is h omega, right? H omega. So let me write down for you. H omega is like 1 minus 5. For other points, my h omega is 0, so low pass. So my system response magnitude squared is also a rectangular function in frequency domain. Okay, let me know if you have any question for this stuff. Now we have to calculate this. Use 4.6 to calculate my output signal's energy. Okay, so step 1 for FT, right? Exactly the same, just as I did over there. I only show you how to calculate this lesson too. Now, okay, let's go through this one. Okay, G omega absolute value squared is F times H, right? No problem. F omega magnitude squared is this one. Any problem with this one? You're good, right? So I substitute H omega magnitude squared into this equation. Actually, I did not change my F omega. What did I change? I changed the boundary of my integral. Since H omega is 1, right, so nothing changed. But now it should be from -5 to 5. So if you look at your textbook, maybe this is only tricky thing. A little confused. So now I calculate the integral from -5 to 5 because of this low-pass filter. Any frequency that higher than 5 will be cut off. Next step, 2 is gone because this signal is even symmetric signal. I do the integral, and only one side times 2, right? So I get 1 over pi r 0 to 2 integral of this one. Okay, this one, you look at your appendix 8.5, use the integral table. So I just use the table, substitute my value in it, I get the final answer. Is 0.001 joule. So when your signal pass the low-pass filter, energy less, right? Energy is less. So E of G 0.001 joule. So the tricky thing is why, right? Did I change the boundary because of the low-pass, because of the system?
Why did we drop the 2?
Oh, yeah, because this is even symmetry, right? Even symmetry signals integral. I drop 2 and change boundary, just one side. Previous -5 to 5, now it's 0 to 5.
How do we know it's symmetrical? Is it just because it's a Fourier transform?
No, not because of omega squared. Yeah.
Oh, okay.
Yeah. So omega squared, right? Minus omega will be the same, right?
Okay. Yep.
Right? Yeah.
How did you know that H omega looked like that? Like how did you immediately do that?
Yes. Yeah. Because the problem told us. Yeah. So my system is an ideal low-pass filter with frequency with the gain unit is 1, right? So my gain is 1, and the bandwidth is 5 regions per second. So I know it's a low-pass filter. Cut frequency should be 5, and my gain is 1. So from the question. Yeah. If I'm going to give you quizzes of then I'm going to plot it for you. Okay, so this is 4.4.1. Any other problems, questions? Okay, so after this example, we're done with energy. We're going to talk about power spectrum. Okay, first equation, right? You know, this is the equation how we calculate energy, the power of a power signal, normalized by P. Right? In your homework, you just did this procedure. Okay, now something new. Similar to previous definition of energy spectrum, we have a new definition. Okay, we define power is an integral. Something's integral over frequency domain. So something's integral give us energy, right? So give us power. So we call it power density, power spectrum density. So So in frequency domain, power density, we call it power spectral density, SF omega. SF omega. So this is just definition. Any problems? After done, we're going to talk about how can we find SF omega. We're going to talk about two methods, and later, towards the end of the chapter, we talk about the third method to calculate SF omega. Any problems?
Why do you change the equal sign to like triangle?
Definition. Okay, I know some textbook use define, right? Or maybe this is what. So this is our textbook use triangle or define. Okay. So I showed two equations. They are related with two methods. 4.70 is method number 1. How can I find SF omega? And 4.20 is method number 2. Method number 2. So we're going to show examples. How can I use those two methods to find a given signals SF omega? Okay, I'm going to explain in details during the examples. So let me see. So we're going to show example for 4.20 first, because our textbook uses that sequence. Okay, look at this one. Okay, something familiar, right? This is something we know. This is Fourier series. So if you can find your signals Fourier series for a periodical power signal, find Fn, substitute Fn into 4.20, you'll get SF omega, right? Straightforward. So we're going to use one example, show how can we find Fn and how can we find SF omega based on Fourier series you'll be doing. So I'm going to use this side. Okay. Example 4.2.1. I'm going to use this one, calculate. Okay. If you look at your textbook, you'll get the problem. So we have a signal. Right? We have A cosine of neutrality plus theta. So this one is a periodical signal. Right? Definitely it's a power signal. We want to find the signals SF omega, power spectral density. So based on equation 4.20, we have to find Fourier series Fn. Okay, now let's look at how can we calculate Fn. Previously, we always talk about use the definition, right? Find Fn, use your integral table, find Fn. Today we talk about method number 2. Method number 2, we call it inspection method. So I'm going to go over what is inspection method and how can we use it. I rewrite it by using reequation. Cosine will be the definition of complex exponential. Number one, we use reequation, right? Just split it in terms of complex exponentials. Second step, for this term and this term, they separate them, right? So we have omega 0 t plus theta become ej theta times ej omega 0 t. This is use property of complex, use exponential. Any problem? Now, I want to show you some equation we used before. Remember this one? A signal, periodical signal can be expressed by unlimited summation of complex exponential with different free series as an amplitude. Okay, I'm going to explain this one. F0. So I have unlimited summation of complex exponential with its series. Okay, this one just expansion of this summation sign. Okay, now I'm going to do the inspection. So I compare, right? Now we compare this one and this one. What do you get? Right? This term is this term, right? So I have ej omega 0 t, ej omega 0. So that means f1 is here, right? 2a, half a dj theta. And this term is this term. This term. So red one is the red, green one is the green. How about all others? All others, they are zero. They are not here. So from inspection, we obtain F1 is so I get all other. For n does not equal 1 or minus 1, f equals 0. So I have f1 a over 2, right? Half a ej theta. Half. F minus 1, a half e to the minus 2 theta. Now I know f8, I know my fn, right? I know my fn. I'm going to substitute my fn into 4.20, find my sf omega. So today we talk about third method, how can I find fn. So if the signal can be extended or expanded in such way, right? Complex exponential combination, we can directly find your Fn by inspection. So if I give you a signal, sine, cosine, combine of sine, cosine, you don't have to calculate the integral. You don't have to use the table of integral. Okay, any problem? How can I get my F1, F minus 1? So next we just substitute, right? Fn into 4.1. So same, right? Same, just I give you a little more details compared with solutions of our textbook. So step 1, we rewrite Ft in terms of linear combination of complex exponential based on Euler equation. Number 2, we find my Fn. Number 3, we get substitute Fn into the 4.20. We get power spectral density. So this is my F1, right? F1 square, this is my F minus 1. So we get power spectral density for the sinusoid signal over here. So one thing you can find, power spectral density give us information about the amplitude of your signal, right? Frequency. But phase increasing, right? Phase information cannot be obtained from your spectral density. Okay, this one is if we know SF omega integral through frequency, we get power, right? We get power. So we just review, right? Impulse functions integration is this one. If omega 0 free in this boundary, so we have 1/4 a squared plus 1/4 a squared, we get half a squared. But in your homework, you also proved cosine signals power is half, right? Half a squared.
The inspection method, the comparison is really important, right?
Later you don't have to do the inspection, right? Later you don't have to compare. So ej omega 0t, I know all the thing before it will be my F1, right? E to minus j omega 0t. This part will be my F minus. So how about something like ej2 omega 0t. Here I have something. So I have something here, right? For example, I have gx, for example, 7, 3, 5, 9, 4. Something like, if I have something, right, can be a number, can be a variable. If I have something before it, what is this one? F2, right? So then you don't have to compare. Just look at this one. Okay, this is my F minus 1. This is my F1. So comparing just help you understand how can I get this result. Okay, so 4.20. Step 1, find Fn, right? Step 2, use 4.20, find your SF omega. You are done. And we have another method, find Fn. Okay, any problem, any question about this example?
So I wonder, is that the SF is the same result as the one we got with, like in the handbook?
Yeah. So, what have we? have it. The result can be checked easily in time domain. So this information is also gone, right? So we can you just want to know if I do the time domain calculation, if I still get the same power, right? Is that right? Okay. So for power signal, we have P will be this is the equation which we use. It's a periodical signal, so I don't write limits, right? T goes to infinity. I have a square cosine. Any problem for this one? Okay, so I have okay, this trick we did many times. Half 1 plus cosine 2 omega 0 t plus theta dt. Okay, any problem for this one? Cosine square will be half 1 plus cosine 2 times of your phase angle. So how about the second part? 0, right? 0. Cosine signal equal in whole periods, we always get 0. They get 0. So we have a square over 2t, t over 1 dt. We get a square over 2. So we did many times, right, in our previous examples, and we also did in your homework. So a square over 2, half a square from urgency from zero. The same, right? The same. Any problems? Any questions? So we talked about 4.20. Now we want to talk about 4.17. How can we find SF omega based on 417? So we use the second example to show 4.17. So example 4.2.2. Let me use this one. So we have a signal, right? We have a signal. Ft is A times e to j omega 0 t rectangular t over capital T. Try to find the power spectral density. So 4.2.2. 4.2. Ft is ej omega t 3 times So let me show the 4.17. Okay, based on the problem, we want t is a number and t goes to infinity. So for t is a number, we want to find ft omega also minus 1. So this is a free transform. This free transform is, so let me give you a definition first. So belongs to ft, right? For example, this is ft. ft t is a part of your original signal. How can we choose a part? So we cut length capital T from your original signal. And ft omega is the Fourier transform of this new signals Fourier transform. So yeah. Rectangular T over capital T is like a scissor cut, a part of your original signal. So actually this one is already FTT. So we want to find this signal's Fourier transform, right? You may have different ideas. Okay, this one I have Fourier transform, this one I have Fourier transform. I use convolution, right? But if you look at this one carefully, this one like a frequency shift, right, to original signal. So we're going to use frequency shift property instead of convolution. So now let's go to our So from the table, rectangular signal's Fourier transform is sync. So this is a pair, right? We know, we just use it. Now, signal time complex exponential, we use frequency shift property. So complex exponential time the signal in frequency we shifted by omega 0. This is a property we use. So we get the Fourier transform of this entire signal. It's AT sync with a shift, right? With a shift. So let me write down for you. So FTT. So this is my FT's Fourier transform. Okay, we substitute the FTT omega into 4.17. We get SF omega. Right, so we have A square, right? T square cancel with this T, so only T left, sync square. So my SF omega is A square sync square. So this is my SF omega. This is my SF omega. Power specificity is sync function square. So we can find this is example using 4.17. Any problem? Questions? How can I get this? Now step 2. T goes to infinity. So they have sinc function, right? So now t goes to infinity, right? T goes to infinity. A is already related with t, so we move it outside to this limits. Okay, here t goes to infinity, we have t times this one. Let me okay, sinc square look like this, right? Like this. And the amplitude is t, right? T. Duration is over t times at. So then t goes to infinity. This one will be high, very, very high, right, to infinity. And the duration of this middle will be narrow, goes to 0. So I get a impulse. I get impulse when t goes to infinity. So I get delta, right, omega minus omega 0. Okay, so 4.2.2 is the example show how can we use 4.17. The trick thing will be find your Fourier transform, like the modified Fourier transform. Those two equations, those two methods you can use, but we have a more popular way we are going to discuss very soon towards the end of this chapter. We are going to use correlation method to find power spectral sensitivity, and that one is more generally people use. Okay, the results agree with obtained by Fourier series expression. So if you are interested, you can try to use 4.25 Fn of the signal. And then the result should be the same. Okay. Any problems, question for this one?
On the previous slide, how did you
Yeah.
get the unit impulse from
So sinc function, right? T is my amplitude, right? So look at the picture I showed here. So this is sinc square, right? Sinc square. At is my amplitude, right? Duration is 1 over t. So when t goes to infinity, what do I have? I have a very, very high but very narrow signal. So when t goes to infinity, I have infinity amplitude and 0 duration. So that is the definition of impulse, right?
Okay.
Yeah. So I have a when t goes bigger, I have the blue one. Even bigger, I'm going to have and finally when t goes to infinity, I get impulse. So from the black one to blue one to green one, and if you are more color, going to become narrower and narrower, sharper and sharper. And finally, when t goes to infinity, I get impulse. Okay, so similar what we did for signal goes through a system. For empty signal, if your signal goes through a LTI system, output signals PSD, power spectral density, is input signals power spectral density time magnitude square of your system response. So this is connect your input and output. And if we know Sg omega, right? We can find signal GT's power by integral Sg omega in frequency domain. Okay, so I'm going to stop here. So we talk about two kind of signals of specificity. For end signal, we have